Okay, let's start. Today we will be discussing about rotation trajectory. In the last class, we have talked about joint space trajectory. Then we talked about Cartesian. Joint space means if you provide that how this angle will rotate with respect to time, right? Whether it will go slowly and then speed and then slowly again, or constant speed. No, those depends on how you want to move this joint with respect to time. So that was our joint space trajectory. Then we talked about Cartesian space trajectory, that means how this end effector will move with time, right, like this or like this. Okay, but as we have discussed, even you specify the trajectory with respect to this one, but ultimately control happens here. So every time we must convert to this joint, relative joint, what is the corresponding motion here for this joint trajectory. So first, if you provided joint at say position A and then position B, what is the joint here, then you do the trajectory with respect to this joint space. That means how much angle it has to move in what manner. So inverse kinematics have to be done once here, twice here, and rest of the trajectory will be done with respect to this. But if you do point A to point B, how you want to move this point, this way or this way, so you can calculate at every time step how much it should move, and then corresponding to every time step here you should do inverse kinematics, you should do inverse kinematics, you should do inverse kinematics. So if you do the trajectory planning in Cartesian space, it is important that you have to do the inverse kinematics every time step. But if you do the joint space trajectory, then you just have to know point A and point B. So this is the two differences and corresponding advantage and disadvantage. By the way, here there are a couple of emails from some students regarding the clarifications for their midterm marks. So these following students, I have rechecked their papers, but there is no change. But still, if they want to ask any questions, I have brought their answer scripts with me today. So at 10:10 they should come in the front, and I can tell you that what is the problem in your answer scripts. After that, as usual, the following 8 students will come in the front at 10:15 to have all the clarifications or ask me questions, okay, or I ask questions. For today's lecture, this is uploaded today morning, no, as 26lec.pdf. So having a review of our last lecture, so in the last lecture we have discussed what is the necessity of a trajectory planning, right. Now just to repeat again, I want to move from point A to B. How I want to move, I have to plan and tell the robot this is the way you move, okay, and so that's trajectory planning. Then we have joint space. We have joint space planning. As I told you, the robot moves with respect to the joint motions. So there we have seen a fifth order polynomial is good if you want to put restrictions on your position, velocities and accelerations on both the sides. That means at the beginning and at the end. So since there are 6 conditions to be satisfied, so if you use a polynomial of fifth order, then you will have 6 coefficients can be calculated from those 6 conditions. However, if you put some additional conditions like our difference between the final and the initial is equal to some ratio of velocities, then we have seen that one of the coefficient, that is the a5, becomes 0. So a fourth order polynomial is sufficient for such additional conditions. Then at the end we have seen that how Cartesian position trajectory can be developed, and today we will talk about how a Cartesian rotational trajectory will be developed, because Cartesian trajectory consists of position and rotations. So, in today's outline we will have just a reminder of orientation representations which we have done in our chapter 5. We have seen the Euler angles can be used for orientation. We have seen direction cosines can also be used for orientation, but today we will see a third representation which is called single axis rotation, and we will try to understand its representations, and if I want to do the trajectory planning, how it can be done with single axis rotations. For your information, trajectory planning can be done with respect to these two also, okay, but this one will be simpler. How simpler, I will tell you. Then we will see an example of single axis representation, and then of course the summary. So, in chapter 5 we have seen that a rotation of a rigid body, here we talk about the end effector, can be done with respect to Euler angles and the direction cosines. That means, if there is a frame attached to the end effector, what are the component of those axes on the fixed one, right, just like a rigid body rotations. So, one can use direction cosine, one can use Euler angles. So, if you look at my hand, suppose this is my initial configurations at initial point, and then let us say it changes to another orientation at another point. So, for the position part, that means x, y, z coordinate of the origin of this frame, and coordinate of origin of this frame here, that can be done with respect to the knowledge we have gained in the last class. Today I am talking about if from this orientation, if it goes to that orientation, how to do that. Now, here say I have a global coordinate frame which is the inertia coordinate frame. So, if this is the coordinate frame, so then if this is my x, if this is my y, and if this is my z away from u, so then what is the component of x in this frame will be my first column of the rotation matrix using direction cosine. What is the component of this axis in this frame is my second column of my rotation matrix. What are the components of this unit vector in this frame is my third column of my rotation matrix. So, now in these different configurations, I can also find out what is the x component in the coordinate frame, fixed frame, what are the component in the fixed frame, what are its component in the fixed frame. So, if this orientation x, if you say x initial, so I have 3 values here, y initial I have 3 values here, z initial I have 3 values here. In these configurations, x final I have 3 values here, y final I have 3 values here, and z finals I have 3 values here. Let me show you on the paper how I can represent. So, let us say this is the orientation of the initial, okay, and I may have a global frame here, inertial frame, okay. So, if I want to represent, suppose this is x, y and z. So, if I want to represent this coordinate frame here, apparently they look parallel. So, q initial will be consisting of u x I UYI UZI VXI VYI VZI, then WXI WYI WZI. So this is my initial values. That means if you draw a parallel frame, so I bring this thing here and I draw a parallel frame. So in this case QI looks like 1 0 0 0 1 0 0 0 1 for this configuration. From there I go to new configurations, maybe it is here. Say X, Y, Z, and let us say X final, Y final and Z final. So I can Q final. So now I can have a parallel here. So this is this is this and this is this. So X final, Z final, Y final, and the previous one was XI.
Hello, sir.
Yes.
Can you correct paper slide?
Huh? Yeah.
Hello, sir.
1 minute, wait. Okay, so in this case you can similarly find out in actual.
Hello, sir.
Yes.
Still not correct.
Oh, okay. 1 minute.
Press 2 times. One more. Okay.
Okay. So here also you can in actual scenario you can find out what will be your QF actual values, numerical values, but I am writing in terms of variables UXF, UYF, UZF, okay, VXF, VYF, VZF, WXF, WZYF, WZF. Okay. So now what it means is I have to go from here to here. For the positions I am not talking about, because how to go from this position to these positions, maybe this way. This we have done it in the last class, but I am talking about Q variation, Q changing from this orientation to this orientation, which is from red to this brown. So now what I want to do, I want to move my UX value from this value to this value. I want to move UY value from this value to this value. So now I have initial value and final value. Now in the last class we have understood how to generate a polynomial, no, if I have given you initial and final value. So if you put a condition of velocity and accelerations also on ux and uy, you can think of a polynomial, maybe you can say fifth order polynomial. So for this thing one fifth order polynomial, for this thing another fifth order polynomial, for this thing another fifth order polynomial. So you can think of 9, so 9 fifth order polynomial. So if you use the direction cosine matrix method to represent the rotation from here to there, you may choose 9 fifth order polynomial, but important thing is Qi transpose Qi should be 1, okay, which will be 3 by 3, and Qf transpose Qf should be identity matrix 3 by 3. Now since you are changing it independently, there might be a problem of satisfying this equation. So what I wanted to tell you is, I know rotation requires 3 independent coordinates, but I am using 9 coordinates, so it is difficult. So I write it here, using 9 variables and satisfying is an unsatisfying orthogonality condition, that is q transpose q is equal to 1 3 by 3 is difficult. Okay. So this is one of the difficulties if you use 9 variables, that means direction cosine method. Okay. If you use the Euler angle method, so using Euler angle method, no, three polynomials are sufficient, but numerical singularity may be a problem, as discussed in chapter 5. Okay. So now today we will see a third type, okay, which is in between, which means here I require 9, here I require 3, both has this advantage and disadvantages. So we will do some trade off, okay, to see that, okay, not all 9 I have to calculate, not I will have singularity. Let us see a third approach. So you go to the slide. So here I come, so with respect to the n values perform trajectory planning like the joint space. So the second statement I have explained you in terms of one component of direction cosine variable. Now the third point here is corresponding motion in reference frame is difficult. Okay. Difficult means, of course, if you are practicing frequently it may not be so difficult, but otherwise, 3 coordinate frame, its components, or 3 Euler angles, is difficult. So as I said, there is a trade off. So we are talking about a third approach, which is the next one. So third approach is using a single or double axis rotation. So this is the concept like this. Let us understand the single axis rotation. Okay. Look at my hand. So this is one configurations, right? Let's go there. Okay, this is one configuration, and this is another configurations, right? Let's repeat. This is one configuration and this is another configuration. Now this configuration, as per the single axis rotation, the theory says that I can find out an axis and then I can rotate about this axis by certain angle to reach to the new position. I repeat, I have a coordinate frame here, I want to go there. In earlier knowledge we came to know it can be used using direction cosine from here to there or Euler angles, but today we are learning the third approach, that from here to there can be achieved by a rotation about an axis, which is my pen here, by certain angle. So a rotation of a frame from one configuration to another configuration can be obtained by a pure rotation about an axis. So the question is, what is that axis? So, in case of double axis it is the same concept, but rotation has to be twice. Okay. We will not talk about double axis, we will talk about the single axis. The following methods are effective in avoiding this difficulty. What is this difficulty? Difficulty is this one. Corresponding motion in reference frame is difficult to understand intuitively because it is given in as a combination of different time varying axes. I am talking about disadvantages of these two methods. Disadvantages of these two methods are it is difficult to understand, and then other difficulties which I mentioned. To avoid this, we introduce single axis. So, if it is a single axis rotation, then the first method, that means single axis rotation, is based on the representation of rotation about a fixed axis. So, the questions will be, what is that fixed axis which we will study today? This double axis we will not do it, so I am skipping the third point. So, this is a single axis rotation, a representation of the relation between frame A and frame B having the same origin is given by this pair E, a vector quantity, and alpha, a scalar quantity, and this vector quantity E has Ex, Ey and Ez. E is the equivalent axis of rotation and alpha is the equivalent angle of rotation. Let us stop here for about 5-10 seconds and reread it. A representation of the relation between two frames FA and FB, two frames are indicated as FA and FB, having the same origin, can be given by a pair. This pair means 4 scalar numbers, 3 scalar for the component of E, 1 scalar, second scalar, third scalar, which indicates the component of unit vector E and the angle about that axis. I will show you in front in the paper. Let us say this frame is represented by FA, the red one, okay, and then the brown one is represented by FB. Okay. Let me redraw it to have a clear understanding. So, I have let us say this is my frame B, okay, and then this is my frame A. So, the statement which I made is this rotation from FA to FB can be given as a rotation about certain axis E and by an angle alpha. So, from FA to FB, if I can find out an axis E and if I rotate the whole frame about this axis, then I will go to FB. So, this is the meaning of this one. So, this is the frame as I was trying to show you, and if I rotate about this axis here, so this right hand frame, if I rotate it like this by an angle alpha, I will go to the new positions. I repeat, this is my frame here and this is my axis here, okay, and if I rotate it by certain angle about this axis, something like this, I will go to the new positions. So, single axis rotation concept is if I rotate about E by an angle alpha, I will go from FA to FB. So, this E is a unit vector indicating the axis of rotation, okay, and it has a component Ex, Ey and Ez, and this component I mean E in fixed frame, okay, or if I am going from A to B, so it is in frame A. So, this is in frame A, okay. So, since it is a unit vector, since E is a unit vector, we know for a unit vector E transpose E is 1. This is a scalar 1, okay. In other words, Ex square plus Ey square plus Ez square is equal to 1, okay. So, this property we will use it later, but now in this diagram I have explained you how a transformation from one frame to other frame can be represented using a third method. So, this is a single axis rotation, a third approach. And what are the first two approach? One is direction cosine, another is the Euler angle. So, this is the third approach. We will go to the slide now. So, now this pair, that means E, which is the unit vector, and the alpha can also be represented by a 3-dimensional vector E having direction A. This is the same thing what I told you. The way we represent the rotation matrix Q, which is now a function of E and alpha, is given by this formula, that Q E alpha is equal to E x square cos prime alpha plus cos alpha. What is cos prime alpha means? Cos prime alpha is 1 minus cos alpha. Then the next element is Ex Ey cos prime alpha plus Ez sin alpha, Ex Ez cos prime alpha minus Ey sin alpha, and similarly I can find out the second column elements, and finally the third column elements, okay. Now, the question is how this is coming. I will explain you where from this coming, because for direction cosine and for Euler angles we had certain physical understanding of from where this Q matrix comes. So, now for this one also I will tell you how it comes, okay. Okay. For that I will go to the again to the page. Okay. First thing is, let us say this is my coordinate frame x, y and z. The unit vectors are I, j and k, okay. It has moved to a new positions, x prime, y prime, z prime. It has a I prime, j prime, and k prime, okay, and this from I j k I define that it has happened due to this rotation, and using our direction cosine we know this is nothing but I prime j prime k prime represented in the, say this is my fixed frame f, okay. Now suppose if I have a point P, if I have some point P in frame F which is indicated with a vector r1, okay, and I am giving a rotation to it about certain axis, let us say E, okay, this is E here, and I have rotated in this direction. So then R1, this R1 has moved to a new position, say here, which is indicated as R2. So this is a new vector R2. So from R1 to R2, so this is the rotation it has happened, right. So R1, which is a vector to represent any point P, R1 rotated by an angle alpha to reach R2. So this rotation is alpha. So this rotation is alpha, which is this, which is this rotation, okay. So some book will give you a derivation of this R2 expression. So R2, so from vector algebra one can calculate R2 is equal to E transpose R1 into E plus cos alpha R1 minus E transpose R1 into E plus sin alpha E cross R1. You might ask where from it comes. I can give you a reference. There is a book by Angeles. It is on robotics. Exact title I don't remember, but it is on so it tells you that how this comes. Now the question still remains unclear that okay, what is Q? Now what I do is, this is a new position of a vector from a old position of this vector. That means if I have initial position of a vector is R1, it goes to new position of a vector R2. So if I can do it for my vector I, that what is the new position of the vector, knowing the old position here, then I can find out the first column. If I find out what is the new position from the old position, using this formula I can find out this one. If I can find out what is the new position of k from the old position, using this formula I can calculate k. So my intention is to do that part now to prove what is your Q matrix, okay. So now I will put R1 is I and I means 1 0 0. Okay. So, I means 1, then I will put R1 is j, I will put 0 1 0, then I will put R1 is equal to k as 0 0 1. Okay. I will show you for one maybe, and other two you will understand accordingly. So, let me now try to do it. So, R2 means new position will be I prime, right. So, I prime is equal to E transpose I E plus cos alpha, I1 mean R1 means I minus E transpose I E plus sin alpha E cross I. Okay. So, E transpose, E has a component Ex, Ey, Ez. I has a component 1 0 0. So, E transpose I 1 is Ex. Okay. Now, similarly E cross I will be how much? So, if you apply those cross product rule, so this will be 0, okay, then it will be minus Ez and this will be Ey. Now, I substitute everything here. So, I prime is equal to E transpose I1 is Ex, then it has Ex, Ey, Ez plus cos alpha, I is 1 0 0, then minus E transpose I is Ex, then it has Ex, Ey and Ez. Okay. Then plus sin alpha, and this is 0 minus Ez, Ey. Now, we continue deriving this thing. So, now what I have is Ex square, these two, plus cos alpha here minus Ex square cos alpha, that is it. The second one Ex, Ey, then this will be minus Ex, Ey cos alpha, then minus Ez sin alpha, and the last one is Ex, Ez minus Ex, Ez cos alpha, then minus Ey sin alpha. So, in Ex, this is Ex square cos alpha. So, we indicated as Ex square cos prime alpha, because cos prime alpha is equal to 1 minus cos alpha. Okay. So, this I am putting plus cos alpha. Here Ex, Ey, and I have Ex, Ey cos alpha. So, this will be Ex, Ey cos prime alpha minus Ez sin alpha, and then this will be Ex, Ez cos prime alpha minus Ey sin alpha. So, what it says is this is nothing but I prime. I prime means this one. So, I has rotated from this position to this position. So, I prime, this is my I prime. So, this is my first column of Q. So, first column of Q I have calculated as this value. Now, you can see in the slide whether this is the same or not. I presume you have written it down. Now I will show you on my slide whether this is same or not. As I compare Ex square cos prime alpha plus cos alpha, Ex Ey cos prime alpha, here I have written Ez, but on this I am coming plus, we will check it, and the last one is Ex Ez cos prime alpha minus Ey sin alpha. So, let us go to the paper. There is a problem here. This comes from this step and then this comes from here. So, E cross I, so E cross I is here, this cross, so this will be 0 0, first one is okay, this thing, oh this is plus Ez because I block this. So, Ez minus 0 and this will be minus y. So, this is plus, this is minus. Okay. So, now so this is plus, this is minus. Okay. So, once I have calculated the first column of Q matrix, similarly I can calculate the Z, similarly I can calculate the second column of Q E alpha as J prime and the third column of Q E alpha as K prime. Okay. So, now you understand that how knowing these expressions, we start from here. If you want to know how this comes, as I told you, you have to look at this book or similar other book, but let us start that we know this, and from there I can find out what is my first column of Q matrix, then the second column of Q matrix and the third column of Q matrix, which I have shown on the slide. So, slide again. So, this is the Q E alpha. Okay. So, the same thing I have written here. Note that Q E alpha is nothing but the new position of I, new position of J and new position of K, where this new position of I prime, J prime, K prime are the unit vector in the x, y and z directions of FB expressed in FA. So, same, let R be an arbitrary vector in FA and R2 be the vector obtained by rotating R1 about E by an angle alpha, and this is the expressions taken from Angeles 2003. And then I have shown you here what I have done on the paper, that R2 if you substitute as I prime, so this is the expressions, you get it, and similarly the other two columns. Now, let us take a practical example. Let the orientation of RF with respect to the end effector frame of R0, RF and R0 are the orientation of a vector. Trajectory from R0 to RF can be given as one of which alpha varies from 0 to alpha. So, what we have understood is a rotation can be defined with respect to a fixed axis rotated by certain angle, let us say it is 0 to I alpha, and 0 to I alpha, 0 to alpha f, if you put a condition like this, that alpha at 0 time is 0, alpha at time Tf is alpha f, similar to what we have done for theta, then one can use a polynomial function which is given here. Okay. So, as I told you, let us see a practical example. So, let us look at a gripper. A robot gripper is shown in this diagram. So, let us say this is the robot gripper placed in this manner. Okay. So, this is your x axis, this is your y axis, and this is your z axis. So, in a way, z axis, along the z axis you have this, the extended arm portion, right, and opening is z. So, this is your z. Now, from this initial configuration, it has moved to another configuration where z has become like this. In other words, this is now parallel to the initial value, which is x0, okay, and then this becomes parallel to y0, okay, and then this one is parallel to z0, okay. So, now let us find out what is the E. So, basically I am looking for a E, actually I should be looking E here, I am looking for a E, and I am looking for a E and an alpha, okay, to see that if I rotate this frame here, about E, I should be able to come to this configuration, okay. So, let us go back. So, as I told you, this Q, that means relationship between the final and the initial is 0 1 0 0 0 1 1 0 0. Let us look at it whether it is right or wrong. So, the xf is parallel to y0. So, Q matrix should be 0 1 0. The first column is 0 1 0, okay, 0 1 0. Let us look at the second one. Y is this one, and that is parallel to z0. So, the second column should be 0 0 1. So, second column is 0 0 1 0 0 1. The next one, the z axis is parallel to x axis here. So, the third column of Q should be 1 0 0. So, the third axis is 1 0 0, 1 0 0. Okay. So, now the question is, this numerical value is given to us, okay, and I want to go from the initial configuration to the final configuration given by Q in time t, which is 1 second, okay. So, now what is that axis and what is that angle? If you look at this expression here, the Q matrix, if you sum the diagonals, let us sum it on the paper. Ex square cos prime alpha plus cos alpha plus Ey square cos prime alpha plus cos alpha plus Ez square cos prime alpha plus cos alpha. So, adding diagonal terms, which is called trace of Q. It is called trace of Q. So, Ex square 1 minus cos alpha plus Ey square 1 minus cos alpha plus Ez square 1 minus cos alpha plus cos alpha. So, Ex square plus Ey square and Ez square sum is equal to 1 because it is a unit vector. Then I have cos alpha, cos alpha, cos alpha plus 3 cos alpha. Then minus, I take cos alpha common, and then I will have again Ex square plus Ey square plus Ez square, which is equal to 1. So, at the end I get 1 plus 2 cos alpha. So, you see, very interestingly, if I add the diagonal terms, there is no Ex Ey component appearing in the final result. So, trace of Q is nothing but 1 plus 2 cos alpha, which will give me the value of alpha, the angle of rotation. So, in our case, we have this matrix. I will show you from the screen, you do not have to go through the screen. So, come to the paper. So, Q is given to us as this one. So, trace of Q, that means summation of all these 3. So, trace of Q is equal to 0, but I know trace of Q is also 1 plus 2 cos alpha. So, for our problem, one plus 2 cos alpha is equal to 0, which will give me alpha is equal to minus half, and that is equal to alpha is equal to 120 degree. So, I know the rotation of the frame should be 120 degree, but then what is the values of Ex, Ey, Ez? For that, I will do the following thing. I have to write down the Q matrix for you. So, I will write down the Q matrix. Ex square cos alpha prime plus cos alpha, Ex Ey cos prime alpha plus Ez sin alpha, then Ex Ez cos prime alpha minus Ey sin alpha, then Ex Ey cos prime alpha minus Ez sin alpha, Ey square cos alpha plus cos alpha, Ey Ez cos prime alpha plus Ex sin alpha. Then I write Ex Ez cos prime alpha plus Ey sin alpha, then Ey Ez cos prime alpha minus Ex sin alpha, Ez square cos prime alpha plus cos alpha. Now, what I am going to tell you is as follows. Suppose if you go along this route, what I am telling is this is my Q32 element, this is my Q23 element, this is my Q13 element, this is my Q31 element, this is my Q21 element, and this is my Q12 element. Let us look at the subtraction between Q23 and Q32. Q23 minus Q32. that means this minus this. So, Ey Ez cos prime alpha minus Ey Ez cos prime alpha will cancel out. So, this will cancel out. Then this is sorry, I have reversed it, 3 2 minus 2 3, Q3 2 minus Q2 3. So, this will cancel out. So, this minus this cancel out. This will be Ex sin alpha, minus and minus will be plus Ex sin alpha. So, it will be 2 of Ex sin alpha. If you subtract this one with this one, so you should be able to find out Ex Ez cos prime alpha, Ex Ez cos prime alpha will cancel out. Ey sin alpha minus and minus Ey sin alpha, it will be 2 Ey sin alpha. So, if I write it here, Q13 minus Q31 will be 2 Ey sin alpha. And now, if you do this thing, Q21 minus Q12, it will be 2 Ez sin alpha. So, now we have an interesting relation which is given here, that E, which has component Ex, Ey and Ez, is actually half into 1 over sin alpha is Q32 minus Q23 Q13 minus Q31 and then Q21 minus Q12. So, now alpha value we know from our previous step. So, this quantity I know, and if I do this operations Q32 minus Q23, Q13 minus Q31 and Q21 minus Q12, so I can calculate what is my E. So, let us calculate that for our given problem. So, what is our problem? Problem is Q is given as 0 1 0 0 0 1 1 0 0. So, alpha we have calculated as 120 degrees. So, that means sin alpha is sin 120 degrees. It will be whatever value it is, we will calculate it, but let us do this one. So, this will be 1 over 2 sin alpha 3 2 minus 2 3. So, 3 2 minus 2 3 is this one, this will be 1 1 3 minus 3 1. So, this is this again 1, and then this will be this one again 1, and sin this thing. So, this will be 180 120. So, this will be root 3 over 2. So, this will become half root 3 over 2 1 1 1. So, I get 1 over root 3 1 over root 3 1 over root 3. So, my E value is 1 over root 3 along x, 1 over root 3 along y, 1 over root 3. So, if this was my it was my x, y, z. So, 1 over root 3. So, if I go along x axis 1 over root 3, I go along y about 1 over root 3, and then I go along z about 1 over root 3. If I join with this origin here, so this will be my E vector, and then if I rotate it from this frame by 120 degrees, I will go to the new frame. So, now I will show you the graphical representation of the frame which is rotated from its original configurations by angle 120 about this axis E. So, that figure I will show you now. So, go to the slide. So, this is the way it will move. So, this is my E axis, there is a mistake, this is not K, it is only E. So, this is E, and if I rotate 120 degree, right, the whole frame from x0, y0 to z0 will come to x, y and z. So, but my interest is trajectory planning. So, this is only the initial and the final configuration, but how it will move? Now, in this case E is not changing, E is a fixed one, only change is alpha. So, let us see how alpha can be calculated. So, here if we say, let us say alpha, the angle will have the same constraints like we have done before, that initially and finally it will have 0 velocity and 0 accelerations. So, we can use a fifth order polynomial, we can use a fifth order polynomial here, okay, and this fifth order polynomial can be given by these expressions. We can check very quickly that when t is equal to 1, so t equal to 1, this is 1200 minus 1800, which is minus 600, and then this is 720. So, this will give you 120. So, which is our final. So, at final it is 120 degrees. Okay. So, what I am trying to do is at some intermediate point, let us say t equal to half second. So, here I am putting an example of the rotation matrix representing the intermediate orientation at t equal to half second, then it can be given by this matrix 2 by 3, 2 by 3, 1 by 3. So, this Q matrix I need it for my kinematics and dynamic analysis, and this is my second column and this is my third column. So, that is the way the trajectory can be incorporated now in a orientation matrix. And again the figure will be similar to what I have just shown. So, you see initially initially Z was oriented in these directions, okay. So, and after rotation it has intermediate position has become like this, and after some time it will be. So, this is about 60 degree rotation I have done it about this axis. So, about this axis this present position is corresponding to 60 degree, because at a half I have calculated. Now, if you keep on rotating this thing, you will reach this configuration like this, okay. So, after this is after half a second. So, this is about 60 degree here, this is 60 degree here, okay, and after 1 minute it will come to this configuration as I have shown you in my. So, I can do it with the highlighter also. So, this is the configuration it will reach after 1 minute, okay. So, with this I want to end this chapter, and so there is a summary. Single axis rotation representation was introduced. Expressions for those rotation parameter, that is E and your alpha, was derived, and an example was also solved for your understanding, okay. So, if you have quick questions you can ask me, otherwise what I will do is next 5-7 minutes I want to show you some video for the applications part. I have 2 more classes left. Next class I will talk about the computer applications or the programming aspects of robots, and the last class I will do the applications, but I have many videos. So, I thought one or two small videos I will show today and rest I will show in the last day. Okay. But if you have quick questions about this trajectory planning or rather rotational planning, you can ask. Otherwise, at 10:15 those three students will come, if they are present today, to have their clarifications for the midterm exam, that is, yes, the names appear there, and after 5-6 minutes, once their clarification is over, these following 8 students will come as per our regular interactions. So, I will wait for 30 seconds for any general questions on today's lectures before I show you the video for some applications. Yes, questions? I can't hear.
No question.
Okay. But those 8 students will have a questions, many questions. Okay, let's watch. This is for arc welding application.
is not the first, but we have developed the most outstanding arc welding robot on the market. The IRB 1600 ID, the ultimate arc welding machine. I've shown you the top 6 sales arguments for the IRB 1600 ID, which are the long life expectancy of the hose package and that it's easy to replace. The IRB 1600 ID has the highest reliability of all process arms on the market, and the slender profile of the robot with hose package makes it possible to have a high robot density on the shop floor, and thus a higher output from the factory. The slender profile and the enlarged work area of Axis 6 ensures excellent accessibility for welding inside narrow places and enables circular welding without interruption or disturbance. The last 2 arguments on increased accessibility makes the programming time shorter for robot installations with IRB 1600 ID than for other robots in arc welding applications.
So, you have seen how a single robot works. Now, let us see how many robots work together. This is for spot welding. So, spot welding of different car bodies. Okay, so that's about two small videos. So now I'll request, if these three students are here, come in the front, and other 8 can wait for about 5 minutes. So Ato Baligus and Agus is here today. Raise your hand.
Absent.
Ato Desaleg and Wagaso, raise your hand. Absent.
It says lead.
Absent.
No,
Where is he?
lead.
Okay, come in the front. Ato Yosef Hailey,
Yes, it is absent.
he is absent. Okay, Ato Desalag, and you have sent me an email, right? Regarding the marks.
Yeah, my doubt was regarding
Okay.
question number 1
Okay.
about the theoretical part.
Okay, let me explain you. Working is a small. I think let's see what answer you have given. It's difficult to see, but here this is question number B. B question number is for when a belt pulley should be used over gears, right? You are writing when the load applied for working is small and for small application of load or power or torque. This is incorrect. We use belt pulley when, zoom. Okay. Yeah, so when the load applied for working is small, so belt pulley is used when you want to take motion over large distance. Okay, this is incorrect, but still I have given you 1 mark. No, just you attempted to write something, and yes, if the load is sometime lighter, you use it, but main important aspect is when you use over a large distance, then only belt pulley is used. Okay, so here you lost 2 marks. Then the C, I am just giving 1 or 2 sample, I am not going to explain all. Now here you are writing to convert signal from C question is why ADC and DAC are required to convert signals from one form to another. That's fine. So for example, ADC converts analog signal, so this part is correct what you are writing, but I would expect that you know the expansion of this thing also. Analog to digital converter, this expansion you should know. Digital to analog converter, this expansion you should also know. So since this expectation I had for all the students, so if I have deducted marks for somebody not writing this expansion, I have deducted for you also. So here you have lost 2 more marks. So 2 to 4 marks you left here. Then here question number E, which is why hydraulic actuator are preferred in robotic systems for large application of load. Yes, that is one correct answer, but there are other correct answer is also for the smooth transmissions and etc etc. So that way you lost, and the major one you lost is here, why position sensor are not preferred to obtain velocity and acceleration. This is wrongly written. This is for error amplification. You are writing position sensor measures the positions angles in an incremental or rotary way in a continuous pattern of motion, not measure the state of position. You are not answering anything actually. The true answer is, if you measure the velocity using position data, you do the differentiation. and differentiation, if there is any noise in the position data, it gives the amplification, okay, and that is the reason it is not used. So it is there in my book also, so please read that part. So there you have the major loss of marks, and I think yeah, so
Okay.
okay, okay, and number 3, of course.
So only regarding
Pardon me.
the theoretical part, but the other part.
Okay, other part, as I given the distribution, this is wrongly done, so you didn't get any point here, and you did not give me the position and information. Just to draw this diagram, as per my scheme, I have given you 2 marks here instead of 5 marks. Okay, are you happy now?
Okay, of course I don't know how I replied to the questions by the time,
Okay.
but I have checked all the questions after that, and by the time I don't, I left my doubts. Thank you.
Okay, okay.
Yeah.
Okay, thank you. So the other 2 students left their opportunities, so maybe I'll just send them email that there is an opportunity today. So this who are present here, Ato Demeke, please raise your hand. Come in the front, Ato Demeke, absent. Okay, Haptamu, Ato Haptamu. Okay, good. Oh, another Ato Haptamu, Shebude. Okay, good. Ato Jevesa, raise your hand. Absent. Okay, good. Ato Kidu, raise your hand. Absent. Ato Liake, raise your hand. Good. Ato Mebrit, raise your hand. Okay, very good. Ato Meheratiab, raise your hand. Okay, so who will ask the first question? Who will ask the first question? Ato Haptamu. Maybe it's not on.
Hello.
Yes, yes.
Okay, I have one question.
Yes.
You have said in the last slide, we can rotate by from old axis to the new axis by 120 degrees.
Right.
How can we rotate? Can you show me?
This is the frame. This is the frame. Can you see my hand? This is the frame. Okay. I calculated my axis. This is my axis, right? I rotate by 120 degree like this. This is my axis. This is my frame. So I connect with my origin and I just rotate. No, this is a fixed object, right? It's like any object. Okay, let me take. I don't have a 3D object which is big, like my book, right? So book has x, y, and this thickness is z. So I have a frame here, and I rotate 120 degree like this. Understood?
Yes, sir.
Okay. Next, who will ask? Please.
Hello.
Yes.
My question is based on the previous section
Okay.
lecture.
Yes.
We are thinking that when we select the controllers again,
Okay.
we are going to let's say we are going to design them.
Right.
Then first we should to put the derivative or the velocity gain is equal to 0.
Okay.
Then based on this, I am not understand the portion. I need some clarification.
Okay. You did not understand. Please repeat the last part.
I need a little bit explanation on this.
Okay. Okay.
design
Okay.
of the
Okay.
gate.
No problem. So let's go to the control, feedback control. Let's talk about this one, simple case, right?
Yeah.
So suppose I want to control the motion of this mass, right? So I have to apply a force. Earlier, in this case, no force was applied. If you displace this object to new position here and you leave it, it will vibrate like this, right? Now I say no, I want to control the position of my mass, so I apply a certain force here. How I apply this force is shown here. So I measure the error, that means desired displacement minus actual displacement. I measure the velocities. Okay, so assuming there is some velocity sensor is sitting here, assuming I have a sensor here to measure the velocity and the position, or I have a position sensor on this and the velocity sensor on this, then I say my force is equal to Kp into the error and Kv into the error. Then for this particular problem, I say okay, my desired displacement is the 0 positions. That means I want to maintain these positions, which means I want to keep these positions here. Suppose if you bring it here, somebody has brought it here, okay, not me, because I have tried to control, but I want to keep it at these positions. So I apply the force. If somebody has brought it here, it will start vibrating like this, but then I will apply a force F so that it comes and stays here. So what is that force? So my desired position xd is 0. So my xd position is 0. xd is 0 means it is kp into minus x. So kp into minus x minus kpx and kvx. Now if I want to keep it there, means what? I want to bring the position to 0. So this is my plot here. So somebody has displaced it, but I want to bring it 0. This is my x. Okay. So if it is 0, then I know this is a formula which has to be satisfied. And in this formula b prime, k prime, I have kv value and kp value. So you know that if b prime equal to 2mk prime, then b value is known to you, k value is known to you. So you choose kv and kp so that this relation is satisfied. In other words, you can bring your system like that. Okay. So depending on how you want to bring your system to the desired positions, you select kp and kp, and there may be many combinations. Okay. one combination you can choose, one combination I can choose, okay. Depending on those combination, maybe it will be like this or it will be like this, all will bring to 0, but these curves will be different for different choices of KV and KP value. Is that understandable? Okay. So, who else next? Last questions. Nobody wants to ask questions? Yeah. Yeah, please.
Hello?
Yes, I can hear you.
Okay. I haven't understand how the single axis rotation representation is better than the Euler representation.
Okay. It is not very. It is better in terms of understanding, because you see in Euler representation what you have to rotate about this axis, then about this axis and about that axis, right. So, to go from one position to another positions, you have 3 rotations, no? One phi, one theta and one psi, but here just one rotation I can understand, okay. In Euler angle I have 3 rotation, 1 rotation, 2 rotation and 3 rotation. So, it is difficult to understand, but here once I calculate the axis, just one rotation I can reach. So, this is the advantage in understanding. Okay, thank you then, see you next week. Okay, bye bye.
That's it.
Yes, more? Yeah, please go ahead.
This is person. Can you check my mid exam?
Yours also?
When I see your checking style, it seems fair. But I want to see again my results.
You want to check your paper also?
Yeah.
Okay, maybe I will go back and I will check and I will tell you next week.
Thank you.
Hello.
Yes?
I have one more question.
Yeah, please.
If you see the diagram for the controllers of the greens,
Background?
the diagram or the figures of the controllers,
Okay.
the proportional, the PD and the PID graph figures.
Okay. Acha, you want
The PD and the
me to show you? No, the figures are not good.
I don't mean not good, but I want to question.
Acha, you want to questions? Okay, okay, just minute, 1 minute. PD, okay. I don't know where it is now. Okay. PD. Okay, here maybe.
I think figure 10.1.
10.1. This one?
17.
17.
10.1.
This one?
Yeah.
Okay,
This one and the next two figures.
right.
In this case, there is the tau d, that means the disturbance of tau.
It's a disturbance from outside.
Okay, and in the previous also there.
Yes.
Yeah. But in the case of the proportional control, there is not here.
You see, I did not show you any disturbance here. You can have a disturbance here also. Okay. What I wanted to tell you is, here you have a you have a P controller here and D controller here. That means proportional controller and derivative controller. What I wanted to tell here is, the derivative controller will not be able to eliminate the steady state error, and steady state error will keep continue there because of the disturbance, because disturbance, if it is continuously there, the steady state error cannot be removed with the position controller or velocity controller, but it can be removed with a integral controller. So here you have position controller Kp, you have a velocity controller Kv, and you have integral controller. So all three controller together in one place. Okay. Okay. Thank you.
Thank you very much.
Yeah. Yes. 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 Okay. Now we can stop the recording, but we can have the discussion. Yes. Please ask me.
My name is Nabi. That is to check the
1 minute. Let me see whether I have written your name correctly or not. Mabrit, right? You can send me email also in case I make a mistake.
number 7.
Okay, good. Okay, thank you.
Hello, sir.
Yes,
Hello.
yes, please.
You make me absent, but
I made you absent.
but I am here.
Okay. Which one is you?
Number 5, Keith.
Okay. So almost one semester gone, still not able to recognize. Okay, you are present. So I'll not bother you next time. You want to ask me something? Please carry on.
No question.
Okay. See you next week.